Hello everyone. Today we will study combinations. A combination is a collection of objects where the order of objects in the collection doesn't matter. A combination is a collection of objects where the order of objects in the collection doesn't matter. What's the difference between combination and permutation? For permutation, it's an arrangement of objects where the order of objects matters. For combination, the order of objects doesn't matter. Let's look at an example to see the difference between permutation and combination. First example, part A. List all possible three-letter permutations. Of letters A, B, C, D. First of all, before we list them, do we know how many elements are there? We're making arrangement for 4 objects out of 3. If we use the formula, it's 4 factorial over 4 minus 3 factorial, which is 24 over 1, which is 24. So now there are 24 different permutations. Let's list them out. Let's list everything out. We have A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. We may have A, B, D, A, D, B, A, C, D, A, D, C. Sorry. B, A, D, B, D, A, D, A, B, DBA, ACD, ADC, CAD, CDA, DAC, DCA, or we may have BCD, BDC, CBD, CDB, DBC, and DCB. That's the 24. Those are the 24 different permutations. How is the combination looks like? Part B. Let's try to take a look on. Let's take a look at the combination. How the combination looks like? Part B. Let's list all possible combinations. List all possible 3-letter combinations of letters A, B, C, D. For combination, the order in the collection doesn't matter. So A, B, C, A, C, B, BCA, BAC, BCA, CAB, CBA. The first column all represent the same collection of letters A, B, C. The entire column all represent the collection of letters A, B, C, since the order of element in the set doesn't matter. The second column all represent a collection of objects A, B, D, because the order of element doesn't matter. Third column all represent the collection of elements A, C, D. The fourth column all represent a collection of elements B, C, D. So here we can see that we have 4 different combinations. Now, how do we compute this number 4? How do we compute that there are 4 different combinations? Observe here. Each collection has 3 elements. Each collection has 3 elements. And when we switch order for these 3 elements, it makes no difference. And here we can see that the number of different ordering for 3 elements is 3 factorial. Or each set, the number of different ordering for 3 elements is 3 factorial. So to get 3 factorial, to get 4 combinations, we can use the total number of permutation divided by the number of different ordering for 3 objects. Take the total number of permutation divided by the number of different ordering for 3 objects, which is 24 over 6 equal to 4. That's how we get 4 combinations. Take the total number of permutation divided by number of ordering for 3 objects. That's how we get permutations. So keep this idea in mind. The number of combination of R objects out of n distinct objects is the total number of permutation divided by R factorial, where R factorial represents the number of different ordering. R factorial represents the number of different ordering. For R objects in the collection. So here I'll take total number of permutation divided by the number of different ordering for 3 objects. That's how I get 4 permutations here. That's how I get 4 combinations here. Let me show you the formula in general. The number of combination of R objects out of n distinct objects is the total number of permutation divided by R factorial. The total number of permutation of R objects out of n is PNR divided by n factorial. This formula can be rewritten as the numerator PNR is n factorial over m minus r factorial over r factorial. If we simplify this formula, it can be rewritten as n factorial over n minus r factorial times r factorial. Keep this formula in mind. That's the total number of combination of R objects out of n distinct objects. Next, let me show you the combination rule. The number of ways to choose R objects out of n distinct objects is n factorial over m minus r factorial times r factorial, denoted by CNR, or the symbol C. This symbol is read C choose R. This symbol is read C choose R. Sorry, N choose R. This symbol is read N choose R. This symbol is read N choose R. So keep this idea in mind. CNR is the same as N choose R. The same as N factorial over m minus r factorial times r factorial. It represents the number of ways of choosing R objects out of n. The number of ways of choosing R objects out of n, where the order in the collection doesn't matter. The order in the collection doesn't matter. Let's look at a simple example first. In how many ways can 5 players be chosen from a team from a basketball team with 12 players? In how many ways can 5 players be chosen from a basketball team with 12 players? So here, when we try to choose 5 players from a team, the order doesn't matter. When we try to choose 5 elements from a team, the order doesn't matter, which means we're doing combination. So use the formula. That's 12 choose 5. We are choosing 5 players out of 12, where the order doesn't matter. Using the formula, we have 12 factorial over 12 minus 5 factorial over 5 factorial, which is 12 factorial over 7 factorial over 5 factorial. Next example. A committee of 5 people is to be chosen from a group of 6 men and 10 women. First question. In how many ways can a committee be formed? A committee of 5 people is to be chosen from a group of 6 men and 10 women. In how many ways can a committee be formed? So, when we choose 5 people from the group, we don't care who we choose first. We care who we choose. We don't care who we choose first. We don't care about the order. If we don't care about the order, this is combination. So we use combination rule. We are choosing 5 people out of a total of 16. We are choosing 5 people out of a total of 16. So the answer is 16 choose 5. There are totally 16 people. We choose 5 people out of 16 to form a committee. We don't care about order. We don't care who we choose first. We care the person we choose. We care about the person we choose. So this is combination. If order doesn't matter, it's combination. So use the formula. 16 factorial over 16 minus 5 factorial times 5 factorial, which is 16 factorial over 11 factorial times 5 factorial. Part B. In how many ways can a committee be formed? If 2 brothers John and Jean must be in the group. In how many ways can a committee be formed? If 2 brothers, John and Jean, must be chosen. So we are choose a total of 5 people. If John and Jean must be chosen, if they must be chosen, we have 3 seats available. We have 3 seats left. There are totally 5 seats. If these 2 people must be chosen, we have 3 seats left. Since there are 16 people, we choose John and Jean already. There are 14 people left. Then we need to form a group. We need to choose 3 more people out of 16, out of 14. So we use 14, choose 3. If John and Jean must be chosen, we have 3 seats available. There are totally 5 seats. If we must pick John and Jean, we have 3 seats available, 3 more seats available. Then there are totally 16 people. If John and Jean are chosen, we have 3 more seats left. So we choose 3 more people out of 14. If John and Jean must be chosen, there are totally 16 people. If John and Jean are chosen, we have 14 people available. We choose 3 people out of 14, which is 14 factorial over 14 minus 3 factorial times 3 factorial, which is 14 factorial over 11 factorial times 3 factorial. Part C. In how many ways can a community be formed? If John and Jean must be chosen, but their mom Linda must be excluded from the group, from the committee. In how many ways can a committee be formed? If John and Jean must be chosen, but their mom, Linda, must be excluded from the committee. So we know the committee has 5 people. If John and Jean must be in the group, must be in the committee, we have 3 seats available. We need to choose 3 more people. But we know there are 16 people. There are totally 16 people. If John and Jean are chosen, we have 14 people left. But if their mom, Linda, is not available, if their mom, Linda, cannot be chosen, we can only choose people out of 13. Total of 13. John and Jean are chosen. Their mom cannot be chosen. So we have 13 more people left. There are 13 people left. We choose 3 more people to form a committee. So the answer is 13 choose 3, which is 13 factorial over 13 minus 3 factorial times 3 factorial, which is 13 factorial over 10 factorial times 3 factorial. Next. In how many ways can a committee be formed? If it must contain exactly 2 men and 3 women. In how many ways can a committee be formed if it must contain exactly 2 men and 3 women? So there are totally 6 men. And 10 women. So let's make choice for men first. 6 choose 2. We have this many ways to choose 2 men. There are totally 10 women. We have this many ways to choose 10 women. So by counting principle, if we have n way to do one task, n way to do a different task, we have a total of n times n way to do both tasks. So we have this many ways to choose 2 men. We have this many ways to choose 3 women. Together we can multiply this together. That's the total number of ways of choosing 2 men and 3 women. By counting principle, we have this many ways to choose 2 men. We have this many ways to choose 3 women. So together, by counting principle, we multiply this together. That's the total number of ways of choosing 2 men and 3 women. So use the formula 6 factorial, 6 minus 2 is 4 factorial times 2 factorial times 10 factorial, 10 minus 3 is 7 factorial times 3 factorial. And use your calculator, that's the final answer. Next. In how many ways can a community be formed? If there is a majority of women in the committee, in how many ways can a committee be formed if there is a majority of women in the committee? This committee has 5 people. If there's a majority of women, then that means it must be more women than men. So there are 3 cases. It could be either 3 women, 4 women, or 5 women. If there's a majority of women in the committee, then it means there are more women than men. It could be 3 women, 2 men, 4 women, 1 man, or 5 women, no men. So there are 3 cases. It could be either 3 women, 4 women, or 5 women. There are 3 cases. If there's a majority of women, then we have 3 cases. Either there are 3 women, 4 women, or 5 women. If there are 3 women, the other 2 must be men. So we choose 2 men out of 6. There are totally 6 men. We choose 2 men out of 6. There are totally 6 men in the committee. There are totally 6 men in the group. And we choose 3 women out of 10. We choose 3 women out of 10. If there are 4 women, it must be 1 man. We are choosing 1 man out of 6. And we are choosing 4 women out of 10. If there are 5 women, we choose 0 men. We don't choose any men. We choose 5 women out of 10. Then add them up. Add them up, we get an answer. And 6 choose 2 is 6 factorial. 6 minus 2 is 4. 2 factorial times 2 factorial. 10 choose 3 is 10 factorial. 10 minus 3 is 7. And times 3 factorial. 7 factorial times 3 factorial. 6 choose 1 is 6 factorial over 6 minus 1 is 5. 5 factorial times 1 factorial. 10 choose 4 is 10 factorial. 10 minus 4 is 6 over 6 factorial times 4 factorial. 10 choose 5 is 10 factorial. 10 minus 5 is 5. 5 factorial times another 5 factorial. Use your calculator, you can get an answer. Next example. In a hand of poker, five cards are drawn from a standard deck of 52 cards. In a hand of poker, 5 cards are drawn from a standard deck of 52 cards. First question. How many possible hands are there? First question, how many possible hands are there? When we draw 5 cards out of 52, we don't care about which card I draw first. We care about what's on our hand. That means order doesn't matter. If the order doesn't matter, we use combination. When we draw 5 cards out of 52, we don't care which card we draw first. We care about the cards on your hand, the cards on my hand. I don't care about which card I choose first. If the order doesn't matter, we use combination. So there are totally 52 cards. I choose 5 cards out of 52. The answer is 52 choose 5, which is 52 factorial over 52 minus 4 is 47 over 47 factorial times 5 factorial. Then use calculator and get an answer. Part B. How many of these hands have 4 kings? How many of these hands have 4 kings? So first of all, let me introduce the standard deck first. It looks like this. In the standard deck, we have 4 different suits. We have spade. Spade looks like this. We have heart. We have club. Club looks like this. We have diamond. Diamond looks like this. So there are 4 different suits. And for each suit, there are 13 different rank. Each suit has ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Each suit has 13 cards. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, and king. Each suit has 13 cards. Jack, queen, and king, they are called picture cards or face cards. Picture cards. Jack, queen, and king, they are called face cards or picture cards. So there are 4 different suits. Each suit, there are 4 different suits. Each suit has 13 different rank or 13 different kinds. Each suit has 13 different ranks or 13 different kinds. How many of these hands has 4 kings? We are choosing 5 cards. If we must have 4 kings, that means we must pick all 4 kings. If we choose 4 kings, we need to choose 1 more card here. So number of ways of choose 4 kings is 4 choose 4. We choose 4 kings out of 4. Out of 4. Then we need one more card. After we pick 4 kings, we need to choose 1 more card to form a 5 card poker hand, a hand of 5 cards. After we choose 4 kings, we need to choose one more card. There are totally 52 cards. If we pick 4 kings already, there are 48 cards left. If we pick 4 kings already, there are 48 cards left. In order to choose one more card, we use 48, choose 1. There are 4 kings. The number of ways of choosing 4 kings is 4 choose 4. After we choose 4 kings, we need to choose one more card out of 48. Since I choose 4 kings already, there are 48 cards left. I need to choose one more card out of 48. And then use calculator, we can answer. Next. How many of these hands have 2 clubs and 3 hearts? How many of these hands have 2 clubs and 3 hands and 3 hearts? 2 clubs and 3 hearts. We know there are totally 13 clubs. We want to choose 2 clubs out of 13. So I have 13, choose 2. We have this many ways to choose 2 clubs out of 13. Then we need to choose 3 hearts. There are totally 13 hearts. We have this many ways to choose 13 hearts, 3 hearts out of 13. So by counting principle, multiply out. We have this many ways to choose 2 clubs. We have this many ways to choose 3 hearts. Multiply together, that's the number of ways of choosing 2 clubs and 3 hearts. Then use your calculator, we can get an answer. Use your calculator, we can get an answer. Part D. How many of these hands have all hearts? How many of these hands have all hearts? We know there are totally 13 hearts. If we want to have a hand of all hearts, means all 5 cards must be heart. So we choose 5 cards out of 13. There are totally 13 hearts. If the hand of 5 cards must be all hearts, that means we choose 5 hearts out of 13. It's 13 choose 5. The order doesn't matter. We're using combination. It's 13 choose 5. Then use your calculator, you can answer. Next. How many of these hands have How many of these hands have 4 of a kind? How many of these hands have 4 of a kind? 4 of a kind means 4 cards with the same rank. 4 of a kind means 4 cards with the same rank. How many of these hands have 4 of a kind? 1, 2, 3, 4, 5. 4 of a kind means 4 cards have the same rank. Means 4 cards has the same rank. For example, we have Jack, 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 and 4 cards with the same rank, and the other card may be different. For example, it may be an ace. That's called 4 of a. That's an example of 4 of a kind. So first of all, let's take care of these 4 cards first. There are 13 different ranks. I first of all choose 1 rank out of 13. Out of 13. Could be the ace, 2, 3, 4, 5. Choose 1 rank out of 13. Then for this rank, we choose all 4 cards. For example, we choose a rank. I choose Jack. As a rank. Then I choose all 4 Jacks. I choose 4 Jack out of 4. So I choose 1 rank out of 13. then choose all 4 cards of this ring. Then for the last card here, then I pick different ring. Next, for the last card, I pick different ring. I cannot pick Jack again. Pick different ring. Say I pick Ace, pick different ring. There will be 12, choose 1. I choose 1 ring out of 12. Say I pick Ace, then I choose 1 ace out of 4. If I pick Ace, there are 4 aces. I pick 1 aces out of 4. So that's an answer. I first of all choose 1 ring out of 13. Then for the first ring, I choose 4 cards out of 4. Next, I choose a different ring. I choose a different ring. I cannot pick the same ring. I cannot choose the same ring again. So there are 12 choices for the ring. I choose 1 ring out of 12. Then for the second ring, I only choose 1 card out of 4. For the second ring, there are 4 cards. For the second ring, there are 4 cards. I only choose 1 card out of 4. And that's an answer. Use your calculator, you can get an answer. Next. How many of these hands have three of a kind and how many of these cards have 3 of a kind and a pair? How many of these hands have 3 of a kind and a pair? 3 of a kind and a pair, it looks like this. Something like this, AAA, BB. 3 of a kind and a pair. It's also called a full house. It's also called a full house. If you play cards, you'll see that it's also called full house. 3 of a kind and a pair. 3 of a kind and a pair. How many of these hands has 3 of a kind and a pair? So, first of all, let's take care of this 3 of a kind first. There are 13 different rings. I choose 1 ring. If I pick 1 ring for this ring, there are 4 cards. I need to choose 3 out of 4 to make 3 of a kind. Now for a pair, I must pick different ring. For this pair, I must pick different ring. So there are 12 rings left. Since I used 1 ring already, there are 12 rings left. I choose 1 ring out of 12. Then for the pair, for the second ring, there are 4 cards. I'm choosing 2 cards to form a pair. That's the final answer. Next. How many of these hands have 2 pairs? How many of these hands have 2 pairs? 2 pairs looks like this. A, B, B, C. 2 cards with the same ring. Another 2 cards with the same ring. A third card with different ring. The third card must be a different ring. So 2 cards with the same ring. 2 cards with the same ring. The third card must be a different ring. How many of these hands have 2 pairs? So let's take care of these 2 pairs first. If we try to form 2 pairs, we must choose 2 rings out of 13. If we try to have 2 pairs, we must choose 2 rings out of 13. Then for each ring, there are 4 cards. I choose 2 cards for each ring to form 2 pairs. There are 13 different rings. I choose 2 rings. Then for each ring, there are 4 cards. I choose 2 cards to form 2 pairs. Then for the single card, I pick different ring. There are 13 rings. I used 2 rings already. So there are 11 rings left. I choose 1 ring out of 11. And for this ring, there are 4 cards. For this ring, for the third ring, there are 4 cards. I choose 1 card out of 4. And that's the answer. Next, let me show you some theorem about combinations. N choose 0 is always 1. And N choose N is always 1. For all N greater or equal to 0. Can we prove it? The number of ways of choosing 0 element out of N objects is 1. If you choose nothing, there's only 1 way to choose nothing. If you choose nothing from the set, there's only 1 way. You choose nothing, don't do anything. And N choose N means the number of ways of choosing all N elements from the set. That represents the number of ways of choosing all N elements out of the set, which is 1 way. We choose them all. N choose N means we choose all N elements out of N. There's only 1 way. We choose them all. This one means we choose none of them. There's only 1 way. Can we prove it? This proof is simple. Use the definition of combination. N choose 0 is N factorial over N minus 0, N minus 0 factorial times N factorial times 0 factorial, N factorial N minus 0 times 0 factorial. N minus 0 factorial is N factorial. 0 factorial is 0 factorial. N factorial and N factorial get cancelled. 0 factorial is 1. N factorial and N factorial get cancelled. 0 factorial is 1. 1 over 1 is 1. And the other one is the same. N choose N. That's N factorial N minus N factorial times N factorial. N minus N is 0 times N factorial. Since N factorial can cancel, 0 factorial is 1. 1 over 1 is 1. Next theorem. N choose R is the same as N choose N minus R. N choose R is the same as N choose N minus R. In a set of N elements, consider a set of N elements. In a set of N elements, suppose we're going to choose R elements. Suppose we're going to choose R elements. What's left is N minus R elements. So the way to choose R element out of N is the same as we kick N minus 1 element out. The way of choosing R element out of N is the same as we choose N minus R element and remove this element. The way of choosing R element out of N is the same as we kick this element out. So the way of choosing R element out of N is the same as we choose N minus R element and remove an element. The answer is the same. So the number of ways of choosing R element out of N is the same as we choose N minus R element and remove it from the set. So this is the same. N choose R is the same as N choose R minus 1. The way of choosing R element out of N is the same as we choosing N minus R element and remove it from the set. So they are exactly the same. Let's prove it. Proof is simple. Left side, N choose R is, by definition, n factorial over n minus R factorial times R factorial. The right side, n choose n minus R is n factorial over n minus R factorial times n minus R factorial. N factorial top minus bottom factorial times the bottom factorial. Then simplify. N factorial stays the same. n minus R, n can cancel. What's left is R factorial times n minus R factorial. You can see that they are exactly the same. They are exactly the same. So n choose R is the same as n choose n minus R. The way of choosing R element is the same as the number of ways of choosing n minus R element. If I remove n minus R element from the set, what's left is the R elements. So keep this formula in mind. Next, before I introduce the third theorem, let's look at an example first. In a group, there are n men and 1 woman. In a group, there are n men and 1 woman. In how many ways can a committee of R people be formed? In a group, there are n men and 1 woman. In how many ways can a committee of R people be formed? So let me show you this problem in 2 ways. First way, by cases. Let me show you the first method. First method, by cases. The group, the committee, it either contains the woman or not. So first method, by cases, is either the woman is either in the group or the woman is not in the group. First case, woman is in the committee. If the woman is in the committee, we must choose the woman. That's 1 choose 1. Then there are n men's. Since I choose 1 person already, I need to choose R minus 1 people. Then we need to choose a total of R people. If the woman is chosen, we need to choose R minus 1 man. Then totally n men. This is n choose R minus 1. That's first case. Case 2, the woman is not in the committee. Case 2, the woman is not in the committee. If the woman is not in the committee, we must choose R men out of n. We must choose R people out of n men. So if a woman is not in the committee, 1 choose 0, we don't choose any woman. There are n men, we choose R men, we choose R member out of n men. 1 choose 0, 1 choose 0 is 1. So we have n choose R. Together, since there are 2 ways to form a committee, we add them up. Since there are 2 different ways to form a committee, add them up. So the answer is If I use the first method, my answer is n choose r minus 1 plus n choose r. That's when a woman is in a group, in a committee. That's when a woman is not in a committee, adding up. That's the number of ways that's the number of ways to form a committee of r people. Method 2 is easier. Method 2 is easier. Method 2. There are totally r plus 1 people. We are choosing r people out of r plus 1. That's easier, using combination directly. There are totally r plus 1 people. M men. So there are totally m plus 1 people. M men, 1 woman. There are totally m plus 1 person. There are totally m plus 1 people. We are choosing r people out of m plus 1. That's using method 2. I use combination directly. There are totally m plus 1 people, and we are choosing r people out of m plus 1. So in this problem, if we use 2 different methods, we get the same answer. If we use 2 different methods, we get the same answer. Means they are the same. They both represent the number of ways of forming a group committee with r people. They both represent the number of ways of forming a committee of r people. They both represent a number of ways of forming a committee of r people. If they represent the same thing, then they must be the same. If they both represent the same thing, they must be the same. Next, can we prove it? Theorem, part 3. N choose r minus 1 plus n choose r equal to n plus 1 choose r. Can we prove it? Let's try to prove it here. Let's try to prove left side equal to the right side. Left side, we have n choose r minus 1 plus n choose r. It can be, let me use the formula. It can be rewrite as n factorial over m minus r minus 1 factorial top minus bottom factorial times the bottom factorial plus the second one, n factorial over m minus r factorial times r factorial. When we try to add 2 fractions, we try to make denominator the same. So let me simplify the first fraction first. Then I try to make denominator the same. The first fraction can be rewrite as m minus r plus 1 factorial r minus 1 factorial plus n factorial m minus r factorial r factorial. We try to make denominator the same. So what I can do here is for the first fraction, if I multiply the top and the bottom by r, then this part will be r factorial. Imagine this. For the second fraction, if I multiply top and bottom by m minus r plus 1. Then this part will be m minus 1, m minus r. This one will be m minus r plus 1 factorial. Then the denominator will be the same. Once I make denominator the same, I can add the numerator together. I can keep the common denominator and add the numerator together. So common denominator is n minus r plus 1 factorial times r factorial. Numerator is r times n factorial. Distribute, I have n minus r. m minus r plus 1 can be rewritten as m plus 1 minus r factorial. Let me explain this first. Distribute first. I have n times n factorial minus r times n factorial plus 1 times n factorial. Distribute n factorial to each of them. Then r times n factorial can cancel. R times n factorial can cancel. It can be rewritten as n times n factorial plus 1 times n factorial, which can be rewritten as n plus 1 times n factorial. I can factor n factorial out. I get n plus 1 times n factorial on the top. On the bottom, m minus r plus 1 factorial can be rewritten as m plus 1 minus r factorial times r factorial. The top can be rewritten as m plus 1 factorial. Bottom is m plus 1 minus r factorial times r factorial. This is the same as m plus 1 choose r. This is the same as m plus 1 choose r. Using combination formula, this is the same as m plus 1 choose r. This is the right side. So here I prove that I make the left side equal to the right side. That's the proof. Next, based on these theorems, let me show you the construction of Pascal triangle. For Pascal triangle, in the first row, we start with a number 1. In the second row, we start with 2 1s. In the third row, we have 1 in the front, 1 in the back. For a number in the middle, we use 1 plus 1, that gives me 2. For the third row, we have a 1 in the front, 1 in the back. 1 plus 2 is 3. 2 plus 1 is also 3. In the fourth row, we have 1 in the front, 1 in the back. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Next row, we have 1 in the front, 1 in the back. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And so on. We can get the entire triangle. That's called the Pascal triangle. What's the theory behind this? What's the theory behind this? In the first row, let me show you the theory behind this. In the first row, we can treat n equal to 0. In the first row, I can treat n equal to 0. Second row, I treat n equal to 1. Third row, n equal to 2. Next, n equal to 3, n equal to 4, n equal to 5, and so on. I can treat my first number 1 as 0 choose 0. Because any number choose 0 is 1. So I can treat my first one as 0 choose 0. In the second row, I can treat my first one as 1 choose 0. Any number choose 0 is 1. I can treat my second one as 1 choose 1, because n choose n is 1. Next row, I can treat my first one as 2 choose 0, because n choose 0 is 1. I can treat my last one as 2 choose 2, because 2 choose 2 is 1. Now, for the middle, I can treat my middle as 2 choose 1. 2 choose 1 is 2. 2 choose 1 is 2. And the reason I can put 2 choose 1 here is because this theorem. N choose n minus n choose r minus 1 plus n choose r is n plus 1 choose r. If I treat n is 1, r is 1. If I set n equal to 1, r equal to 1, I have 1 choose 0 plus 1 choose 1 equal to 2 choose 1. That's why I'm allowed to add these two numbers to get the middle number here. That's why I'm allowed to add 1 choose 0, 1 choose 1 to get 2 choose 1 in the middle. Next row, I can treat number 1 as 3 choose 0. I can treat my last one as 3 choose 3. For the middle, for the number in the middle, if I add these two numbers, 2 choose 0 plus 2 choose 1. If I add these two numbers, what do we get? 2 choose 0 plus 2 choose 1. Using the same theorem. If I treat my n is 2, r is 1. If I treat my n is 2, r is 1, I have 2 choose 0 plus 2 choose 1 equal to 3 choose 1. So 2 choose 0 plus 2 choose 1 is 3 choose 1. And next, 2 choose 1 plus 2 choose 2. If I treat my n is 2, r is 2, I have 2 choose 1 plus 2 choose 2 equal to 3 choose 2. So 2 choose 1 plus 2 choose 2 is 3 choose 2. Next row, I can treat my first one as 4 choose 0, my last one is 4 choose 4. For the number in the middle, 3 choose 0 plus 3 choose 1, using the same formula, I have 4 choose 2. 3 choose 1 plus 3 choose 2, using the formula, I have 4 choose 3. 3 choose 2 plus 3 choose 3, using the formula, I have, that's 4 choose 1. 4 choose 1, 4 choose 2, and 4 choose 3. And same thing for the last row. 5 choose 0, if I use the same thing, apply the same formula. 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. That's the construction of Pascal Triangle, and that's the theorem behind Pascal Triangle. This theorem, these three theorems allow us to add a number to get the next row. Next, let's observe the Pascal Triangle. The sum of the first row is 1. The sum of the second row, 1 plus 1 is 2. The sum of the third row, 1 plus 2 plus 1 is 4. The sum of the next row, 1 plus 3 plus 3 plus 1, this is 8. The sum of the next row is 16. The sum of the next row is 32. It looks like number 1 can be written as 2 to the power 0. Number 2 can be written as 2 to the power 1. Number 4 is 2 to the power 2. Number 8 is 2 to the power 3. Number 16 is 2 to the power 4. 32 is 2 to the power 5. So it looks like, by observing this formula, it looks like n choose 0 in the nth row. In the nth row, n choose 0 plus n choose 1 here we guess in the nth row we guess that n choose 0 plus n choose 1 plus n choose 2 plus n choose n equal to 2 to the power n. First row is 2 to the power 0, second row is 2 to the power 1, 2 to the power 2, 2 to the power 3. So in the nth row, we guess we have n choose 0, n choose 1, n choose 2, up to n choose n. That equal to 2 to the power of n. Is this always true? Let's look at another example. In a school of n students, the students are asked to join a summer camp over the summer break. If the attendance is not mandatory, in how many ways can a summer camp be formed? Let me show you the first method to solve this problem. If an attendance is not mandatory, that means everyone has a choice. They either go to the summer camp or they don't go to the summer camp. So the summer camp may have 1 student, 0 student, 1 student, 2 student, at most n students. So let's consider there are n cases. The summer camp may have 0 student. It may have 1 student, only 1 student. It may have 2 students. It can have at most n students. So there are n cases. The summer camp may have 0 student, 1 student, 2 students, at most n students. If the summer camp has 0 students, in how many weeks can the summer camp be formed? If the summer camp has 0 students, in how many weeks the summer camp can be formed? If there are 0 students, we are choosing 0 students out of n. If the summer camp has 0 students, we are choosing 0 students out of n. The number of ways to choose 0 students out of n students is n choose 0. If the summer camp has only 1 student, in how many weeks can the summer camp be formed? If the summer camp has only 1 student, in how many weeks the summer camp can be formed? There are totally n students. We are choosing 1 student out of n. That's n choose 1. If the summer camp has only 2 students, in how many ways the summer camp can be formed? Very similar. We are choosing 2 students out of n students. And order doesn't matter. The order doesn't matter. We use combination. And similarly, in how many ways the summer camp with n students can be formed? That's n choose n. So that's all the cases. Since that's all the cases, the number of ways of forming the summer camp is, we add them up. N choose 0 plus n choose 1 plus n choose 2. That up to n choose n. That represent the number of ways that a summer camp can be formed. the number of ways that the summer camp can be formed. Let's think of a different way. Let's try to solve this problem in a different way. Consider a second method. There are n students. Each student has two choices. They are either join the summer camp or they don't join the summer camp. There are two choices. Each student has two choices. Either they join the summer camp or they don't join the summer camp. Each student has two choices. And there are n students. Each student has two choices. There are n students. So number of ways to make choice is 2 to the power n. We can get an answer in a different way. There are n students. Each student has two choices. They can choose either join the summer camp or they don't join the summer camp. Each student has two choices. So by counting principle, there are n choices for the first student, n choice for the second student, n choice for the n student. That's 2 to the power n. The total of number of ways is 2 to the power n. That's the total number of ways that a summer camp can be formed. Since we are getting the same answer using two different techniques, since we're answering the same answer, we're answering the same question using two different techniques. This answer represents the same thing, so they must be the same. Since these two answers represent the same thing, they must be the same. So let's also suggest n choose 0 plus n choose 1 plus n choose 2 plus n choose n equal to 2 to the power n. Since these two answers represent the same thing, they must be the same. Since these two answers represent the same thing, they must be the same. Can we prove it? This suggests the same thing as we draw Pascal triangle. Can we prove this answer? Let's try to prove it. Theorem number 4. N choose 0 plus n choose 1 plus n choose 2 plus n choose n equal to 2 to the power n for all n greater or equal to 0, for all integer n greater or equal to 0. For all integers n greater or equal to 0. Let's prove it by induction. Basic step. Assume the statement is true. Let's verify that the statement is true where n equal to 0. Verify the statement is true for first n. First n is n equal to 0. Let's verify the statement is true for the first n. For n is 0, left hand side is 0 choose 0. 0 choose 0 is 1. By this theorem here, every number choose 0 is 1. Right hand side, we have 2 to the power 0, which is also 1. So for the basic step, left hand side equal to the right hand side. That's the basic step. Next, for the inductive step, we assume the statement is true for k. Assume k choose 0 plus k choose 1 plus k choose 2 plus k choose k equal to 2 to the power k. Assume the statement is true for k. We try to verify that the statement is also true when n equal to k plus 1. So here we want to prove that the statement is true when n equal to k plus 1. When n equal to k plus 1, we have k plus 1 choose 0 plus k plus 1 choose 1 plus k plus 1 choose 2 plus k plus 1 choose k plus 1. The second last term is k plus 1 choose k, and the last term is k plus 1 choose k plus 1. That equal to 2 to the power of k plus 1. So we try to prove this statement. So let's try to prove either left hand side equal to right hand side or right hand side equal to left hand side. Let me start from the right hand side. 2 to the power of k plus 1. Right hand side equal to 2 to the power of k plus 1. That can be rewritten as 2 to the power 1 times 2 to the power k. That's 2 to the power k plus 2 to the power k. Because for every integer, for any number, 2x is the same as x plus x. 2y is the same as y plus y. Therefore, 2 times 2 to the power k is 2 to the power k plus 2 to the power k. So 2 times every number is the number plus itself. Now, we use induction hypothesis. 2 to the power k. By induction hypothesis, 2 to the power k is k to the power k choose 0 plus k choose 1 plus k choose 2 plus k choose k. So 2 to the power k is k choose 0 plus k choose 1 plus k choose 2 plus k choose k plus another 2 to the power k plus another 2 to the power k. So plus another k choose 0 plus k choose 1 plus k choose 2 plus k choose 3 in the first row. Last term is k choose k. The second last term will be k choose k minus 1. So another 2 to the power k is k choose 1, k choose 2, k choose 3, k choose 3. The last term is k choose k. Now if I add them up, the first term, k choose 0 is 1. Second term, k choose 0 plus k choose 1. What's k choose 0 plus k choose 1? We're going to use this theorem here. If I let n equal to k, let r equal to 1, what do we get? If I let n equal to k, r equal to 1, I have k choose 0 plus k choose 1 equal to k plus 1 choose 1. If I let this statement is true for all n and all r. If I let n equal to k, r equal to 1, I have k choose 0 plus k choose 1 equal to k plus 1 choose 1. So k choose 0 plus k choose 1 is k plus 1 choose 1. Next term, k plus 1 choose k plus 2. If I let n equal to k, r equal to 2. If I let n equal to k, r equal to 2, what do we have? I have k choose 1 plus k choose 2 equal to k plus 1 choose 2. If I let n equal to k, r equal to 2, I have k plus 1 choose 2. K choose 1 plus k choose 2 is k plus 1 choose 2. Next, k choose 2 plus k choose 3. If I let n equal to k, r equal to 3. That's k choose 2 plus k choose 3 equal to k plus 1 choose 3. So k choose 2 plus k choose 3 is k plus 1 choose 3. Similarly, for the second last term, k choose k minus 1 plus k choose k. If I let n equal to k, r equal to k, what do we get? If I let n equal to k, r equal to k, I have k choose k minus 1 plus k choose k equal to k plus 1 choose k. If I let n equal to k, r equal to k. So k choose k minus 1 plus k choose k is k plus 1 choose k. Last term, k choose k is 1. K choose k, n choose n is 1. This is true for all n. So k choose k is 1. And we know that number 1 can be rewritten as n choose 0 for all n greater or equal to 0. So number 1 can be written as n choose 0 for all n. If I let n equal to k plus 1, number 1 can be rewritten as k plus 1 choose 0. Number 1 can be rewritten as k plus 1 choose 0. And similarly, last one can be written as, we can use this formula here. N choose n is 1. This one I can write as k plus 1 choose k plus 1. I let n equal to k plus 1. Last one can be written as k choose 1 k plus 1 choose k plus 1. This match the left hand side. This match the left hand side. This match the left hand side. So right hand side equal to left hand side. This statement is true for all n. This statement is true for all n, proved by mathematical induction. Next, let's observe some polynomials. How do we expand the polynomial a plus b squared? A plus b squared can be rewritten as a plus b times a plus b. Then when we have two binomials multiplied by each other, we distribute. We can distribute every element in the first parenthesis into every element in the second parenthesis. If we distribute, we have a times a plus a times b plus b times a plus b times b. Here we see that we have 4 terms. We have 4 terms where every term has 2 factors. So every term has 2 factors. And each factor could be either a or b. There are 4 factors. There are 4 terms. Every term has 2 factors, where each factor could be either a or b. And we know that when we multiply, the order doesn't matter. A times b is the same as b times a. So we have a squared plus twice ab plus b squared. When we multiply, the order doesn't matter. ab is the same as ba. So we have a squared plus twice ab plus b squared. Next, let's observe a plus b to the power 3. Let's observe a plus b to the power 3. If we expand a plus b to the power 3, we have a plus b times a plus b times a plus b. How do we distribute? We distribute every element in the first parenthesis into the second parenthesis and into the third parenthesis. It looks like this. Let me show you. A times a times a. That's a. Next, a times b. That's a, b. Next, a times b times a. That's a, b, a. Next, a times b times b. That's a, b, b. Then we distribute B. Then we distribute B here. I have B times A times A. That's BAA. B times A times B. That's B times A times B. That's BAB. Next, B times B times A. That's BBA. Next, B times B times B. That's BBB. So when we distribute three binomials, we have A terms. When we distribute three binomials, we have A terms, where each term has three factors. And each factor could be either A or B. Each term has three factors. And every factor could be either A or B. Again, when we multiply, order doesn't matter. I got A to the power 3, A squared B, another A squared B, AB squared, A squared B. When we multiply, order doesn't matter. AB squared plus AB squared plus B to the power 3. Since order doesn't matter, these three terms looks exactly the same. A squared B looks exactly the same. We have A cubed plus 3A squared B plus 3AB squared plus B cubed. Does this number look familiar? 1, 2, 1, 1, 3, 3, 1. Does this number look familiar? If you remember, you can see that this number looks like the numbers in a Pascal triangle in the second row. 1, 2, 1, where n is 2. We have coefficient 1, 2, 1. Where n is 3, we have coefficients 1, 3, 3, 1. Is this coincident? Is this a coincidence? Let's try to compute A plus B to the power n. Let's try to compute A plus B to the power n. What will you get? If we distribute, we will have n terms. It will be n terms. If we multiply out, it will have how many terms? A plus B to the power 2, we have 4 terms. A plus B to the power 3, we have 8 terms. So A plus B to the power n, it will have 2 to the power n terms. If we multiply out, you have 2 to the power n terms. And each term will contain n factors. So if I multiply A plus B to the power 2, there are 4 terms. Each term has 2 factors. When we multiply A plus B to the power 3, it has 8 terms. A is 2 to the power 3. And each term has 3 factors. It will contain n terms. For A plus B to the power n, if I multiply out, you have n terms. You have 2 to the power n terms. And each term will contain n factors. And each factor will be either A or B. Each factor will be either A or B. So if we multiply out, we have A plus B times A plus B times A plus B times A plus B. If we multiply out, we choose one element from each set for each term. for each term, we choose one element from each set and multiply together. In how many ways can we obtain a to the power n? The number of ways to obtain a to the power n is, if we try to obtain a to the power n, means I need to choose a from each parenthesis. That means we choose letter b 0 times. That means we choose letter b 0 times. If we choose letter a n times, that means I pick a from each parenthesis. If I pick a from each parenthesis n times, that means I choose letter b 0 times. That's the number of ways of choosing letter b 0 times. The number of ways to obtain a to the power n minus 1 times b. For the term a to the power n minus 1, choose b. We choose one factor from each parenthesis. We choose letter a n minus 1 times. So one of them must be b. I choose b from one of these parentheses. The number of ways of choosing 1b is n choose 1. I may choose b from the first parenthesis, second parenthesis, third parenthesis. The number of ways of choosing b is n choose 1. The order doesn't matter. The number of ways to obtain a to the n minus 2 times b squared is, I choose one factor from each parenthesis. And we choose letter a n minus 2 times. We choose letter b twice. So the order doesn't matter. I can choose letter b from the first one, the third one, or the third one, the first one. Order doesn't matter. I can choose letter b from the first parenthesis, the third parenthesis, or the third parenthesis, the first parenthesis. Order doesn't matter. So number of ways to obtain a to the n minus 2 times b squared is n choose 2. If we continue the process, the number of ways to obtain b to the power n, that means we must choose letter b. That means we choose letter b from each parenthesis. That means we choose letter b n times. To obtain the number of ways to obtain b to the power n means we choose letter b n times. So the number of ways n choose n. Therefore, we can see that the coefficient of a to the power n is n choose 0, since we have this term once. Since we have this term this many times. So the coefficient of a to the power n is n choose 0. The coefficient of the term a to the power n minus 1 times b is n choose 1. Since we have this term this many times. Same thing, the coefficient of a to the n minus 2 times b squared is n choose 2, because we have this term this many times. And we have b to the power n this many times. So if we expand a plus b to the power n, we have n choose 0 times a to the power n, n choose 1, a to the n minus 1 times b to the power 1, n choose 2 times a to the power n minus 2 times b squared, plus n choose n times b to the power n. So that's the expansion of a plus b to the power n. Can we prove it? This theorem is called the Binomial Theorem. Let's prove it. Binomial theorem says for all integer n greater or equal to 0, a plus b to the power n is always the summation I from 0 to n. N choose I. N choose I times a to the power of m minus I times b to the power I. This theorem is called a binomial theorem. Let's prove it. Let me first of all expand this formula. If we expand this sigma notation, that means a plus b to the power n equal to n choose 0, a to the power of n, b to the power 0 is 1, plus n choose 1, a to the power n minus 1, b to the power 1, plus n choose 2, a to the power n minus 2, b to the power 2, plus n choose n, a last term is b to the power of n, a to the power n minus n is a to the power 0, a to the power 0 is 1, last term is b to the power n. If we expand the sigma notation, that's what we have here. Can we prove it? We can prove this using mathematical induction. We can prove this using mathematical induction. So, first step, basic step, let's verify that the statement is true for first n. So for basic step, verify that the statement is true for first n. When n is 0, a plus b to the left hand side, a plus b to the power 0 is 1. Right hand side, we take the summation, we plug in 0 here, plug in 0 for n. I from 0 to 0, that means we have 0 choose 0. I from 0 to 0, only take I equal to 0. N 0, I 0. A to the power of 0 minus 0. B to the power 0. 0 to 0 is 1. A to the power 0 is 1. B to the power 0 is 1. So right hand side is also 1. So when n is 0, left hand side equal to right hand side. Next, inductive step. Assume the statement is true when n equal to k. Assume the statement is true when n equal to k. Assume a plus b to the power k equal to k choose 0, a to the power k, k choose 1, a to the power k minus 1 b, plus k choose k times b to the power k. Assume the statement is true when n equal to k. We try to prove that the statement is also true when n equal to k plus 1. We want to prove that a plus b to the k plus 1 equal to k plus 1 to 0 plus a to the k plus times a to the k plus 1 plus k plus 1 choose 1 a to the power k times b plus the last term will be k plus 1 choose k plus 1 times b to the power of k plus 1. The proof is very similar to the previous theorem. The proof is very similar. The left hand side is a plus b to the power of k plus 1. That can be rewrite as a plus b times a plus b to the power of k. If we use induction hypothesis, a plus b to the power k can be rewritten as k choose 0 times a to the power k, k choose 1, a to the k minus 1 times b plus k choose k times b to the power of k. So that can be rewritten as k choose 0 a to the power k plus k choose 1 a to the power k minus 1 times b. Next term should be k choose 2 a to the power k minus 2 times b squared. The second last term will be k choose k minus 1 a b to the power k minus 1. A b to the power of k minus 1. Last term will be k choose k times b to the power of k. Now we distribute a and b to each term in the parentheses, then combine like terms. Let me distribute a first. If I distribute a, I have k choose 0 a to the power k plus 1, k choose 1 a to the power k times b, k choose 2 a to the power of k minus 1 b squared. The last term will be k choose k a times b to the power k. Next, let me distribute b. If I distribute b, I have k choose 0 a to the power k b. Let's line up the coefficient. If I distribute b, I have a to the power k times b. Let's line up the like terms. Line up the like terms. Next, I have k choose 1 times a to the power k minus 1 b squared. For the second last term, if I multiply b here, I have k choose k minus 1 a times b to the power k. For the last term, if I distribute b to the last term, it will be k choose k times b to the power of k plus 1. Then if I add them up, k choose 0 is 1. I have 1 times a to the power of k plus 1. K choose 1 plus k choose 0. By serial number 3, that's k plus 1 choose 1. A to the power k times b. K choose 2 plus k choose 1. That's k plus 1 choose 2. A to the power k minus 1 b squared. The second last term, k choose k plus k choose k minus 1 will be k plus 1 choose k a b to the power k. Last term, k choose k is 1 times b to the power k plus 1. And we know that number 1, by serial number 1, number 1 can be written as k plus 1 choose 0. K plus 1 choose 1, a k times b. K plus 1 choose 2, a to the power k minus 1 b squared. K plus 1 choose k, a b to the power k. And number 1 can be rewritten as k plus 1 choose k plus 1, b to the power of k plus 1. Let's match the right hand side. Here. So that's the proof by induction. This is a proof of binomial theorem. We prove it by mathematical induction. So in general, when we expand the polynomial a plus b to the power a, we can see that the coefficient match the coefficient in the Pascal triangle. The coefficient match the coefficient in the Pascal triangle. So in general, if we try to expand a plus b to the power n, we can use the coefficient in Pascal triangle, then multiply to these terms. A to the power n, a to the power, so the power of a goes down by 1 from n to 0. Power of b increased by 1 from left to right, from 0 to n. This is called the Binomial Theorem. Next, let's look at another theorem. Let S be a set with cardinality of S equal to n. That means in set S there are n elements. Then the cardinality of the power set of S is 2 to the power n. That means in the power set of S there are 2 to the power n elements. Let's prove it. So let S be a set with n elements. Then for all subset of S, if A is a subset of S, cardinality of A may be 0, 1, 2, or n. If A is a subset of S, A may have 0 element, 1 element, 2 element, at most n element. Since S has n elements, a subset of S can have at most n elements. Next, let T0 be the set of A in S such that cardinality of A equal to 0. Let T1 be the set of A in S such that cardinality of A equal to 1. Let T2 be the set of A in S such that cardinality of A equal to 2. And similarly, let T sub n be the set of A in S such that cardinality of A equal to n. Then we know that T0, T1, T2, and Tn, they are subsets of the power set of S. Because in T0, every element is a subset of S, and the power set of S contains all subsets of S. So T0 is a subset of power set of S. In T1, every element is a subset of S, and power set of S contains all subsets of S. Therefore, T1 is also a subset of power set of S. Similarly, all these sets are subset of power set of S. And also, T0 union T1 union T2 union Tn equal to the power set of S. Power set of S contains all subsets of S. Every subset of S may have 0 element, 1 element, 2 element, at most n elements. So if I combine all these sets together, I get a power set of S. In addition, these sets T0, T1, T2, they are all disjoint sets. Because if cardinality of A is 0, it won't be 1. If cardinality of A is 1, it won't be 2. So by definition, all these sets T0, T1, T2, they are all disjoint sets. So we say T0, T1, T2, and Tn, they are mutually exclusive. That means they are all disjoint sets. Since the union of T0, T1, T2, Tn is power set of S, and these sets T0, T1, T2, Tn, they are all disjoint sets, then by cardinality rule, cardinality of T0 plus cardinality of T1 plus cardinality of T2 plus cardinality of Tn is the cardinality of power set of S. since they are all disjoint sets and their union is power set of S. By one of the cardinality rule, the sum rule, it says cardinality of all these sets together is the cardinality of the power set of S. In order to understand this relationship better, let me show you an example. Then this formula will be more clear to you. For example, let S be a set of 4 elements, A, B, C, D. Let's first of all write down the power set of S. Power set of S contains all subsets of S. Since S has 4 elements, subset of S may have 0 element, 1 element, 2 element, 3 element, at most 4 element. The set of 0 element is an empty set. The set of 1 element is the set of A, the set of B, the set of C, the set of D. The subset with 2 elements, it may contain AB, AC, AD, BC, BD, CD. Those are the subsets with 2 elements. The subset with 3 elements may contain A, B, C, A, B, D, A, C, D, and B, C, D. Those are the subset of S with 3 elements. And the subset with 4 elements is the set of A, B, C, D. So those are subsets of S. Together, it's called the power set of S. Power set of S contains all subsets of S. Now, T1 represents the subset of S such that each element has 0 elements. T1 represents the subset of subsets of S such that each element contains 1 element. So in this example, T0 is the set of subsets that contains 0 element. Here it's empty set. T1 is the subset of S. It's a subset of S. It's the set of subsets of S, which contains only 1 element. So T1 contains the set of A, the set of B, the set of C, the set of D. T2 is the set of subsets, which contains only 2 elements. So T2 is the set that contains AB, AC, AD, BC, BD, and CD. T3 is a subset of S, which contains 3 elements. So T3 is the set of A, B, C, A, B, D, A, C, D, B, C, D. T4 is a subset of S, which contains 4 elements. So T4 must be the set that contains A, B, C, D. That's T0, T1, T2, T3, T4. And here we can see that if we combine T1, T2, T3, T4 together, I get a power set of S. And we can also see that the set T0, T1, T2, T3, T4, they are disjoint sets. And the cardinality of T0 plus cardinality of T1 plus cardinality of T2 plus cardinality of T3 plus cardinality of T4. Here we can count that. In T0, there's only 1 element. In T1, there are 4 elements. In T2, there are 6 elements. In T3, there are 4 elements. In T4, there's only 1 element. And power set of S. In power set of S, if we count the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We can check they are the same. 1 plus 4 is 5, 5 plus 6 is 11, 11 plus 4 is 15, 15 plus 1 is 15, 15 plus 1 is 16. So they are the same. So here we can see that cardinality of T0 plus cardinality of T1, cardinality of T2, T3, T4 is the cardinality of power set of S. That explains what does this formula means. Next, let's try to compute cardinality of T0, T1, T2, and Tn. What does cardinality of T0 means? Cardinality of T0 represents the number of subsets of S which contains 0 elements. T0, cardinality of T0 represents the number of subsets of S which contains 0 elements. The number of way to choosing 0 element out of set S is n choose 0. Because in set S there are n elements, and every element in TS contains 0 elements. So we choose 0 element out of n. T1, cardinality of T1 represents the number of subsets of S which contain 1 element. So the number of way of choosing 1 element out of from set S is n choose 1. Because in set S there are n elements and we are choosing 1 element out of n. And similarly, cardinality of Tn represents the number of subsets of S which contain n elements. That represents, that's the same as the number of way of choosing n elements out of set S. We know in set S there are n elements. If we try to choose n element out of n, that's n choose n. So cardinality of power set of S, cardinality of the power set of S is cardinality of T0 plus cardinality of T1 plus cardinality of T2 plus cardinality of Tn, which is n choose 0 plus n choose 1 plus n choose 2 plus n choose n. And by a theorem which we learned earlier today, n choose 0 plus n choose 1 plus n choose 2 plus n choose n, that equal to 2 to the power n. If I show you an example, it will make more sense to you. In this example here, cardinality of T0 is 4 choose 0, because in set S there are 4 elements. The number of way of choosing 0 element is 4 choose 0. 4 choose 0 is 1. Cardinality of T1 is 4 choose 1, because in set S there are 4 elements, and we are choosing 1 element out of 4. That's 4. Cardinality of T2 is 4 choose 2. 4 choose 2 is 6. Cardinality of T3 is 4 choose 3. 4 choose 3 is 4. Cardinality of T4 is 4 choose 4, which is 1. So 4 choose 0 plus 4 choose 1 plus 4 choose 2 plus 4 choose 3 plus 4 choose 4 equal to 16. 16 can be rewritten as 2 to the power 4. So in general, cardinality of power set of S is 2 to the power of n. Let's complete the proof.